Okay, welcome to the 18th day of the Rocco Show. Yay! Yeah, right. Okay, we are in block one, and this is HL1. Hmm? Yeah, I'll see if I can find you one. All right, we're going to be talking today about convergent and divergent sequences and series. Convergent and divergent series. Wonderful. Okay, what we're talking about here is adding up a whole bunch of infinite stuff and seeing if that sum adds up to something finite, in which case it's convergent, or infinite, in which case it's divergent. So I have the sum of some series, and this thing has a whole bunch of terms, and we add them all up. If this thing equals a constant, call it m, then it is convergent. If it equals infinity, positive or negative, I should have put. Then it's divergent. Okay, so if I were to just add a whole bunch of ones, ultimately that thing would go off to infinity. So I need my numbers to be small as they keep going. And in fact, they need to be smaller and smaller and smaller at each step. Otherwise, what winds up happening is that things ultimately blow up. And what you're really kind of looking at is you're looking at, if you were to graph your terms, you would start off with something like that. That's one example. I mean, general shape, this is how they usually look when they are converging. Another way they sometimes look is like this. Should draw it like that. All right. They can alternate, or they can all be the same sign. And I've explained this once before, that in order for something to be convergent, there are a number of criteria that kind of have to be satisfied. All right. Ultimately, the biggest one is that they're getting smaller and smaller and smaller. But in fact, they need to be more than just smaller. Okay. Here's an example. Bless you. If I have this, okay, this is a classic example of what is known as the harmonic series. And those of you that are interested in music might want to do a little homework and find out why it's called the harmonic series, and what does it have to do with Pythagoras, and where does all of this, come from? But this, if we were to look at this, and I'm just going to move it down. So we're dealing with 1 over 1, 1 over 2, 1 over 3, 1 over 4, etc. And this guy diverges. All right. A simple way that we can use, a simple test that is very powerful, but not always enough to, not always like the defining answer in every case, is called the ratio test. And we mentioned that, we talked about this once before, but in the ratio test, we have a to the n plus 1 all over a to the n must be less than 1. The ratio of successive terms must be strictly less than 1. If in case, well, actually, that's an important question. What would it be if it was equal to 1? What? Yeah, every term would be the same, right? And then you would be dealing with 5 plus 5 plus 5 plus 5 plus 5 plus 5. And that obviously, when you add them all up, goes to infinity. Okay, it's obviously not going to shrink down and come to us to a nice little number. But this is very useful. And in fact, there are some cases, and I want to point out, if a to the n plus 1 all over a to the n is equal to 1, then the test is inconclusive. And you need to use another test. There are different tests. If it's greater than 1, you can stop right there because it's divergent. Okay, anything that grows as it gets further on down the road is definitely going to blow up. So if it's bigger than 1, then you just know it's divergent. So you have 3 basic cases: less than, equal to, or greater than. And the only one that we really care about is when it's less than, all right? And as we go through the next couple of years, we will be looking at different tests because they require, for some of them require calculus, which you'll learn next year. I'm going to throw some of it at you this year, but not maybe next semester, not now. And there are, like I said, other tests to use besides just this, and they're kind of fun. Before we go too far, I want to introduce to you, if you haven't already seen from last year, this. Does anyone know what that is? What factorials are? Fantastic. Factorials are very, very, they grow very fast, okay? They explode really quickly. If you go to a calculator and you graph x, thank you. If you graph that, it blows up quickly, okay? Well, first of all, 0 factorial is equal to 1. It is defined as 1. And so is 1 factorial, obviously. So we have something that goes like this. Really fast, okay? Really fast. There are things that grow faster, but not many. And in fact, it grows faster than a lot of your exponentials do, okay? So let's test the harmonic series. So if we look at this, and we do the ratio test on him, so my nth term, this is the way you deal with it. You need 2 terms. You need the nth and the nth plus 1 term. So the nth looks like 1 over n. And you could have used any, this is an abuse of a variable. I. And the n plus 1 term is 1 over n plus 1. Okay? Yes? Everyone happy? Great. Now, let's take the ratio test. So n plus 1 all over n. And in this case, all of my terms are positive, so that makes life a little easier. This is equal to, is this greater than 1 or smaller than 1? Well, actually, I should say this. It is greater than 1 because it's 1 all over n plus 1 all over 1 over n. And you do your double rainbow trick, and you wind up getting, actually, n all over n plus 1. Bigger than 1, smaller than 1? It is smaller than 1. And so we actually have a situation here. We have to think to ourselves, is this... Yeah, grab mine. When we have to begin right now with the definition of a limit, yes? I'm looking at any term, and I'm looking at the term before it. Or I could say I'm looking at any term and I'm looking at the term in front of it. Go back to the definition. This. That's what I'm looking at. The nth term and the n plus 1 term. Yes? Where? The nth position. Yes, that is one of the only words in the English language that is 3 letters and contains no syllables. It contains no vowels, has 3 letters, one of the only a few words in the English language that does that. Are we all happy now? We're all happy now? Okay. All right. Now, we have to think about about a limit. And I've talked to you about limits before. When we take a limit, what we're doing is we're saying to ourselves, what happens as I go towards infinity? All right. Now, let's look at this for a moment. As n gets huge, what happens to this? Well, let's take a small example. Let's take n equals 3. So 3/4. And then we'll look at the next term. 4/5. Well, this is 0.75, right? This is 0.8. What's happening to it? They're getting closer to 1, right? I mean, if you plugged in 100 over 101, it's very, very close to 1, in fact. Okay? Very, very, very small difference between that and 1. And if you plugged in 1,000,000 over 1,000,001, come on now. Really? That's kind of ridiculous. You're basically talking about 1 at that point, right? So here, in this case, as n gets bigger and bigger and bigger and bigger and bigger, you're getting closer and closer and closer to 1, and you're adding 1 every single time, right? Does this thing converge, or does it diverge? If I'm adding 1, basically adding 1 every time, you're getting bigger and bigger and bigger each time. You're not shrinking that addition each time. It's not getting smaller and smaller and smaller fast enough. Okay? Think about the 3 possible cases. You're sitting, okay, we've all gone to the beach and we've all played in the sand. Situation 1, you're digging faster than the sand pours in. You're digging a hole. 2 rates are happening. First rate is you digging the sand out. The other rate is the sand flowing back in. If you dig fast, your hole will get bigger because you're digging faster than the sand flows in, right? Second situation, you're digging at the same speed as the sand is falling in. It stays the same size, right? Or third situation, you're nonchalantly walking over and taking a handful out every couple of minutes or so, and by the time you walk back the next time, it's basically all been filled in, all right? Thank you. So what's going on is that in the third case, you're not removing it fast enough for there to be a hole remaining, okay? Does this make sense? Do you see this analogy? So what you have to think about when you're looking at a fraction or a rational function, where you have a function over a function, like a polynomial over a polynomial kind of thing, and we've all graphed those, right? I mean, if we look at those graphs, a lot of them looked like, some of them looked like this, right? Where you had, like, say, for example, 1 over x, or x squared plus 3x minus 2 all over x to the third plus x squared. Remember this? And you graphed all of those a million years ago, algebra 2. You had graphs that looked like this. You had other graphs that looked like this. Right? Remember that? Where the horizontal asymptote was at a constant. Okay? And then there was the third case that looked really weird, and it went like this. Something. Remember these? Well, first of all, if I just move everybody around for a second. If I did that, you would get this graph. And if you want, pull out a calculator and check. Because you have three situations going on. You have the numerator getting bigger, faster than the denominator and numerator both being even, or the denominator growing faster than the numerator. It's either top-heavy, even, or bottom-heavy. Three situations. And when I say top-heavy or bottom-heavy or even, I'm talking about these coefficients, these exponents. Okay, you have three situations: growth, flat line, or decay. All right? You don't even really need much of the other terms. The other terms kind of create these weird effects. For those of you who have pulled out a calculator, is it looking kind of like that? Yes? Okay. Because you have to understand what a fraction really is. When a rational function. You're dealing with a tug-of-war between a numerator that's trying to make this thing grow and a denominator that's trying to drag this thing down. Okay? You have the flow of sand that you're pulling out of the hole and the rate of sand flowing back into the hole. The numerator makes it blow up. The denominator makes it shrink. Okay? As this function, if you just look at each one of these polynomials, if we look at my numerator of this rational function, if I plug in a really, really, really big number, or let's start small. If I plug in a really small number, like 1, okay, I get 1 to the fourth, which is 1, plus 3, plus minus 2. Okay, so these other terms, the 3x and the negative 2, were important. They really changed the value of that numerator. Okay, but let's just say I plug in 10. Okay, not far away from 1. I get 100 plus 30 minus 2. Now all of a sudden, it's to the fourth. I get 10,000 plus 30 minus 2. Okay? So now all of a sudden, that 3x term isn't nearly so exciting anymore. Right? And that negative 2, who cares about that? That barely affected the overall, growth of my numerator at all. So as I get bigger and bigger and bigger and bigger, these other terms, these secondary terms, they're less important than the first term that has the biggest exponent. Does that make sense? Okay, and imagine if you plugged in a really big number, none of this matters at all. And in fact, what happens is that only the first terms become important at all. Now, if my numerator, if we were to take this thing, and I've just made a total mess out of my whole, there we go. I'll just rewrite it. So we have ax to the m plus stuff all over, where a is just a constant, bx to the n plus stuff, right? Because that stuff doesn't really matter too much, yeah, in the overall grand scheme of things. Now, we have three situations. Bottom heavy, meaning that n is bigger than n. That means my denominator is growing really fast, faster than my numerator is growing, okay? And in that case, if I have a really big denominator, if I'm dividing by something huge, the value is very small, right? If I divide 10 by 1,000,000, I get a really small number, okay? And then in this case, the value drops off to 0, okay? So in this case, my horizontal asymptote is y equals 0. All right. Now, if I have m and n both being equal to each other, then they're even. Then, yeah, sure, this can be weird behavior close to 0, because near 0, small values are going to be affected by those other terms, and we don't care. But as I get bigger and bigger and bigger and bigger, and I go off to infinity, yes, the little terms fall away, and all I'm left with is this front leading term. And we wind up with a situation, and it would look like, you know, example. All right. Well, as you get huge, this happens. All of that goes away. Because like we said, those little terms become unimportant. And all we're basically looking at is this. And then, since they're basically the same size, this happens. And that becomes my horizontal asymptote. You get the ratio of the coefficients. So if that's the case, then your horizontal asymptote is y is equal to a over b. Now, on the third case, that's now when things go really wonky. Because my numerator, when m is bigger than n, when my numerator is growing fast, now all of a sudden my denominator can't keep up, and my numerator is growing so fast that no matter what my denominator tries to do, it can't pull it down fast enough, and ultimately you wind up having a situation where your values go off to infinity. And you wind up with what's called an oblique asymptote. You have and that's the situation that I drew before, where the thing just goes off to the races, really fast into the positive infinity. Now, the ratio test is trying to find bottom-heavy things, okay? Because if you have bottom-heavy things, then you will eventually go down to infinity. Go down to a constant. because each term gets smaller and smaller and smaller and smaller and smaller to 0. And that means if I added them all up, they're all so small that they ultimately all add up to one constant rather than keep adding on to each other and going bigger and bigger and bigger. So let's try this one. Let's take an example. My glasses. Sorry, guys. Thanks. Let's try so we're going to find what a to the n and what a to the n plus 1 look like. This is 1 all over 2 to the n plus 1. Excuse me. And now we divide them. We do the double rainbow. And what do you think we can do here? If we can, but how can we do that? Okay. Now, as this thing gets bigger and bigger and bigger and bigger, does that plus 1 count very much? No. And in fact, when that goes away, I'm left with 2 to the n all over 2 times 2 to the n, and then what happens? What happens? Right. They just fall away. So my ratio test says what? Does this converge or diverge? It converges because it's smaller than 1. And in fact, what we can even say is that my terms are getting about half as big each time. They're getting smaller and smaller and smaller by 2 each time. All right. Now, let's try another one. Ooh. That's fun. Try that one. See what happens. Sometimes it's even easier just to plug it in and see what happens. Plug in your first few terms. Who's bigger? The numerator is bigger, isn't it? Is it going to converge or diverge? It's going to diverge. And you can confirm it because if you do, I mean, like, first of all, this is equal to 4 plus 3 all over 2, 4 plus 9 all over 4, right? 4 plus 27 all over 8. What's happening? It's getting bigger, isn't it? Each term is successively larger, isn't it? And that means that if I add up things that are getting bigger, it's going to blow up and become an infinite sum. And you can confirm it with the ratio test. So you would have 4 plus 3 to the n plus 1 all over 2 to the n plus 1 all over 4 plus 3 to the n all over 2 to the n. And let's simplify a little bit. And as n gets bigger and bigger and bigger and bigger, what happens to the 4 and the 8? They fall off. They become so unimportant. You know, if I plug in 100, 3 to the 100th is big. 2 to the 100th is big. Adding 4 and adding 8 to it is like kind of an afterthought. And you wind up with and then that becomes that. Each term gets larger and larger and larger and larger and larger. So this guy diverges. All right? Are we cool? All right. So I want to pause on ratio test and send you all to the boards with some logarithm practice. So this episode of the Ronco Show has been brought to you. Oh, wait, hold on. There's one thing I want everyone to know first. If I have log of x plus log of 5 equaling log of 2, I don't care. I'm making this one up. And you want to get rid of those logs to get x. You can't do this. The rule that you're going to use is, this is base 10, right? Or base 7, let's make it 7. Fine. I cannot do this. You can't do that, okay? You can only use this rule, rule 7, which I showed you the other day, when you have a log equaling a log. So you have to use rule 2, 3, maybe, whatever rule it was. Now you can use that rule. Okay. You must condense it to log equals log before anything else is done, okay? That's an important step. And this episode of the Ronco Show has been brought to you by the Ratio Test.